we have another talk this month. Normally we just have one joint talk, but because the talk in December was cancelled and postponed to January, now we have the pleasure to have two talks in January joint between UKSPS and Formal Methods for Security Network. And today it is my pleasure to introduce a distinguished professor with whom I had the pleasure to work, Ramanujam from Institute of Mathematical Sciences in Chennai, but also visiting at Azim Premji University in Bangalore. And some of you may know Jam, some of you not, but for those of you who know him, I'm sure that you know that he's contributed extensively in automata theory, epistemic logics, theory of distributed systems, game theory, aspects to do in general with theoretical computer science. And also he's contributed to the Association of Symbolic Logic in India and other associations to do with logic in India and not only. And aside for this very academic theoretical computer science work, he's actually been awarded in 2020 a National Indian Award for Science Popularization by the Indian National Science Academy for the work that he's been very passionate about and has been doing for over 3 decades in science communication and mathematical education for school children in India. And today we're going to have the pleasure to hear a talk about the first part, which is applying logics to security to express insecurity in this case. And without further ado, Jan, thank you for accepting the talk, and the floor is yours.
Thank you, Yana, and thank you, Siam, for this invitation. And for this kind introduction as well. Thank you very much. It's a pleasure for me to be here and giving this talk. And so one thing before I begin is to say that please interrupt me anytime, stop me, and questions need not wait until the end. Okay, let me share screen. Now, I hope everyone can see the screen. I've not gone into full screen because, this way I can at least get to see some, the gallery, so that in case I need to, if there is somebody making a noise, I can find out. Okay, thanks. Okay, so thanks again. And so today's topic, I said insecurity, going from terms to formulas. And this is going to be very much from the perspective of a logician looking at security, insecurity problem from a logical perspective. And so the broad outline is introduction and security problem with the term algebra that we normally use and the symbolic verification of security protocols, and then looking at the same problem when we also extend terms with formulas. So what is all this about? So the idea is that, so first introduction, now to me, the holy grail in reasoning about security, when we talk about logics for security, is something like temporal logic. Now, propositional temporal logic has been remarkably successful in the design and verification of reactive systems. So much so, Moshe Vardi calls it from philosophical logic to industrial logics, right? So these are industrial logics now, and temporal logic provides a requirement specification language that's abstract and yet allows room for complex control properties, and has been shown in the last 20 years for especially for hardware verification, protocol verification, and then also increasingly in software verification. Now, one problem is that PTL is, propositional temporal logic is very good with control properties, but not with data. Handling data is in general difficult. And also, the finite state abstraction, even with over infinite duration systems, which works very well, go for a toss when you go to data. So now, okay, that's a comment on PTL, but what about logics for security? It would be very good to have a similar logic, some abstract logic for reasoning about security. Now, what are the requirements of logics for security? Now, control properties, it turns out, are not very crucial. In fact, not even data, but you do want data, but not data as such, but patterns in data are central up to cryptography. And this is at the heart of symbolic verification of security protocols, where we look at communicated messages as terms in a symbolic representation, terms in a symbolic algebra, and we make the perfect encryption assumption so that we assume that intruder cannot break cryptography, but we do have data. So patterns in data are very important for reasoning about security. Now, there is a kind of case to be made to say that we don't especially want temporal properties, for a good reason that, in security verification, you're talking about an intruder who is all powerful sitting there and collecting terms. So, and once you can collect all terms, time really doesn't matter. You really want to look at violation of security occurring at some state. And from there, you can sit and try to reconstruct all the knowledge that has been gained. So intruder knowledge is kind of monotone, it keeps increasing. So you can say it's kind of timeless. So, the only kind of temporal flow that is important is that when you receive a message, it has been sent earlier, right? So there is a kind of a causal connection that's important, but time really doesn't play that much of a critical role. So what plays a critical role in reasoning about security? I've already said you do need to handle data, you do need to talk about patterns. So what is it that's a central requirement if you were to look for a requirement of a logic for security? Now, this is something that from the 80s people have been talking about. One is propositional logics of knowledge. Epistemic logics provided early hope for reasoning about security. In fact, I would say the 80s were kind of dominated by that, and it's easy to see that, I would say maybe going into the 90s, right? Reasoning about knowledge and ignorance is really indeed central for security theory. And knowledge provides a very nice propositional abstraction of saying, A knows that B doesn't know that, C knows that, and so on, etc. And that makes a lot of sense. Of course, the problem is that in the case of cryptographic protocols, the devil does hide in the details, and coming up with the right abstraction, knowledge provides a beautiful abstraction, but knowledge combined with things of the form, when you're talking about terms and variables, bindings, substitutions, all kinds of things go wrong. On the other hand, if you don't have all that, you can't really reason about cryptographic protocols. So coming up with the right abstraction has been a challenge. And, it's not that there are no attempts. We do indeed have many logics proposed and studied. I have personally worked with Suresh and former students. We have proposed some logics. But rarely do we find the versatility and simplicity of temporal logic with its tools. Of course, as yet, there is no reason to give up hope. And there is, I would still say that epistemic logics do provide a good abstraction. But what is it? Clearly, propositional logics of knowledge do not suffice. And it's not simply a matter of mixing knowledge and time, because the time is not the critical thing here, but you've got other stuff, bindings, substitutions, and so on going on. How do these things interact with it? Now, having said that, I'm not going to go much into epistemic logic in this talk, but if you start thinking in such terms, that how do we analyze these interactions? Well, you need to go dig a little deeper, go further down, and that's what this talk is going to be about. But abstractly, if this is what we start and say that epistemic logic is a good abstraction, and how do I logicize what is going on, in terms of one-way functions or the underlying cryptographic ideas? Well, cryptographic protocols raise many challenges for epistemic reasoning. One is, for instance, treating a nonce or a key as some abstract, uninterpreted data item, that would be good, but it does not work because most of the trouble relates to different instantiations of these. These are not single items. Every session, you have a different nonce, right? And so they are not rigid identifiers in the language of modal logic. And so you can't treat them as rigid identifiers. You have to have some other mechanism. And then when I receive a message, according to the protocol, some M encrypted with K. Do I know that I have received M? No, of course, only if I have whatever, the inverse or some way of looking into encryption. Well, do I know that I have received something encrypted with K? Not clear, because, and this is the fundamental problem with security, right? Of course, do I even know that I have received some encrypted message if I don't have access to the inverse key, or in general, if I don't have K inverse, it could be junk, right? I mean, it could be just some bit sequence that I have got, right? So if you want to talk about epistemic reasoning, this kind of detail creates enormous complications. And do these questions mean the same when we refer to the intruder? Well, I think these are, I mean, we can fix all these, but things turn ugly in the process. And this is the point I'm trying to make, is that you don't have a simple, elegant logic for which you can develop tools and apply. A lot of details go in, and a lot of work. I mean, people here, I'm sure, many tools have been developed. There's a lot, but tools with epistemic reasoning, all that become harder and harder as we go along. So finding that right abstraction is what. So here is one that we can think of. Technically, a very clean and very simple logic, which actually, in which you can say a lot. For instance, consider a propositional logic, but with infinite connectors. So you have negation, and you don't have binary disjunction, but you have OR over some countable set. And then diamond A alpha, that you have to read it as I do some action A, maybe communicate something, after which alpha holds. Another is to say agent A knows alpha holds. Now, this logic is actually very interesting, because you can talk about A knows that it's one of these out of some infinite set of assertions. So, and I mean, I have said countable, whatever, some index set. So the main point is that you can start distinguishing some infinitely many worlds. And why do I talk about infinite disjunctions at all? Think of encryption. See, when you encrypt something, when you're hiding data out there, you can think of this abstractly as an infinite disjunction. And out of that, when you do decryption, you're taking conjunction with infinitely many cases and removing them, yielding a unique one in the process. Think of it as you have P or Q, and then you have negation Q, taking conjunction with that yields P, right? This is the fundamental principle, except that, finite stuff, fixed stuff doesn't work. You need some abstracts. Now, actually, with infinite disjunctions and epistemic modalities, you can describe lots of one-way functions that occur in the literature in general. Actually, this is a coding that is that you can undertake and do. I have done some work on a logic like this. It's very expressive, and of course, we need finite presentations. It's not clear, and of course, there are no algorithms for any such logic, right? So, but then that's the first clue, and then the second way is to say that wherever you have infinite disjunctions appearing in logic, much better is to use quantifiers, right? I mean, quantifiers in general give you better syntactic control rather than this kind of connectors. Okay, so that means that you want to look at a quantified logic, and so you can start with some atomic propositions, and you have some monadic predicates, unary predicates, equality on, I've just put variables. This is usually the pure logic, and you can have assertions of the form there exists infinitely many witnesses for X, or unboundedly many witnesses for X, such that alpha holds, which is really the encryption, the idea of encryption. And then another one which says there exists a unique X such that alpha holds, which is what decryption usually amounts to, right? So once again, you can take a logic like this, and I have personally sat and worked out a whole lot of one-way functions, express them in logics like this, and then you can reason with logics of this kind. Again, very quickly things become very nasty. I mean, no hope of things like decidability, working with decidable theories, etc. in such logics. Again, all this is by way of background to say that quantification, assertions, equality on terms are all very important, and combined with whatever assertions that you want to make about security. So if you're really looking for abstractions, these are ways of thinking, that's all. So there are many interesting security properties like zero knowledge proofs can be expressed. What we really want for one-way functions, right? If you're talking about cryptography, is really not infinite disjunctions, but large disjunctions, right? You want to say there are too many witnesses for X for any particular principle. And, you don't know how to do that. And we don't have good logics for reasoning, expressing this kind of complexity theoretic ideas. And so therefore we say infinite, but then of course, the logic is undecidable, which is of course not surprising. And finding a decidable fragment, which is expressive enough to describe one-way functions in the abstract form is a real challenge. So, if we want to look at underlying reasoning and cryptographic protocols, saying encryption works and capturing these things logically using, logical resources like quantification or, infinite disjunctions, etc., is something of an interesting exercise. How far can we go and capture, complexity theoretic assumptions relating to one-way functions and so on? I think it's a principal challenge for talking for logic for security. Please again interrupt me if there are any questions. I'm just making some general remarks. So what is very clear is that you do need to bring in communicated terms, right? Here I just said variables x, y, and then you talk about x, but there exists x. But what is x? X is going to be bound to some term, and those terms come from some term algebra. And we do need to bring it into the logic. So we want the basic propositions that we begin with to have at least assertions on equality on terms, right? And these terms arising from the underlying Dole-Yao model. I'll formally present it, but these are the standard way of doing symbolic security verification. So, forget knowledge. Even if you take a very simple logic where you have equality on terms, what are terms? Terms, you have some variables, maybe you have keys, and you have pairing, and you have encryption. Now, you can do constructed keys, you can go into, instead of K, you have arbitrary term T prime. You can do a lot more, but my point is not so much to talk about any particular term algebra. You can start looking at distributive encryption, where encryption distributes over pairs. You can have blind pairs, homomorphisms. Term algebra can be strengthened as you want. My point here is going to be to show that even with a very minimal term algebra, there are important logical issues to resolve. And I think that's what I'm after. And so you have something like atomic formulas like equality on terms, and then you have negation, disjunction, and then you have existential quantifier, right? Or quantifiers. So this is simply a first order logic, right? There's not even knowledge, there is nothing. It's a first order logic to do simply equational reasoning on terms. And with this, you can talk about any particular protocol state, right? If you're talking about runs of security protocols, any reachable state, any particular state, you can talk about it in terms of these. And note that already, you have interesting patterns. For instance, if I say there exists X and a Y such that X encrypted with Y equals T, this says that, okay, I know, not I, but, it talks about knowledge of the pattern in T, right? So patterns in data can be represented with basically some quantified logic. Now, and this is the fundamental idea, but then, this kind of logic right here, when you look at equational theories, even with very simple, add just a couple of atomic propositions and the logic is undecidable. And that's, it's first order logic after all, right? With boundary relations of some kind, and not very surprising. Now, but the key point I want to make is that if you look at knowledge of the form, T has a pattern, which is actually an encryption, right? That's what it says. Now, this will be available to principals as well as the intruder at protocol states. So then, well, if you can communicate terms, you can communicate this knowledge as well, right? So it makes sense to extend the term algebra with assertions of this form. So you can say that, so why not? I mean, at a particular state, a principal sends a term, something in the term algebra, but it can also send a certificate. It can say that, hey, I can guarantee you that this is an encrypted term, right? Going back to the original challenge that I was talking about, when I receive a term, do I know that it's even an encrypted term? Well, somebody can certify it for you. Well, and that certificate can be verified independently, which is, that is at the heart of, for instance, zero knowledge proofs, right? And and there are various kinds of certificates used in security theory, and wherever authorities certify something, you can't look into details, but the certificate tells you that the term that you are looking at has certain property. For instance, in the case of a voting protocol, we often look at, for instance, it's a binary voting protocol. I can assert that V is, I'm sending a term V, and it's either 0 or 1 without, I can certify that without saying which it is, right? So, a lot of, a whole lot of such things it actually makes sense, right? So we look at this, so this idea that what happens if you start communicating assertions of this form, right? Very limited assertions, equality on terms, existential quantifier, maybe combinations of this kind. And now, as I said, this thing is useful for applications, but I don't want to take it up for the discussion here. I want to look at it purely from a logical viewpoint. What is the impact of that from a viewpoint of reasoning, from a viewpoint of complexity of logics, etc., and studying the impact of communicated assertions on the reasoning process itself. So the idea of communicating formulas is indeed standard in logics. For instance, in dynamic epistemic logic, one sublogic called the logic of public announcement, you look at protocols. Basically, at any point of time you announce something, basically you make an announcement of a formula, and that takes the entire system to a new state, because people take whatever is the assertion and look at only that submodel where the assertion is true. So these are actually model transformations. And the main point is that something like that is happening in security protocols as well, except that the kind of formulas that we are talking about and terms that we are talking about come from a very specific structure. And this interplay is what makes this logics very interesting and also challenging as well. So specifically, we study the insecurity problem in the presence of assertions. Okay. To recall for everybody, what is the insecurity problem? In general, you have a security protocol. I'm not defining security protocols, etc. I'm assuming that this is something that we can take as background. Is there an execution of a given protocol that leaks a designated secret? Fundamental problem. And the protocols can be represented as a finite set of rules. Each rule is a finite sequence of pairs. I can simply write it as, if you receive, the ith element says, if you receive something R, then after that you send something S, right? If I receive something in general, then SI is the message I send. And I have said from the intruder, we'll get to that. And, these R's and S have variables that are instantiated by agents in some particular session. For instance, when I send something, I can instantiate, send, an abstract communication in the protocol with some particular, maybe a fresh nonce, right? And why are we talking about messages being received from the intruder? We assume that there is this intruder who can look at everything in the network, can block messages, can pretend to be somebody else, can forge messages, but cannot break cryptography. And so we might as well assume that every message sent is actually going to the intruder, and any message received is actually coming from the intruder, right? And we say that a protocol is insecure if there is such a run where the intruder can derive a designated secret from the knowledge accumulated in the course of the run. And all these are stated in words, but they can be, formalized and specified precisely. And a run, the big problem, the insecurity problem, is that a run can in general involve arbitrarily many sessions in parallel. In security, this is the heart of the difficulty with verification of security protocols. You can have multi-sessions, and each session may introduce new fresh values or nonces, and the intruder can instantiate the variables with arbitrarily large terms, right? Because somebody who's receiving something, a term which has a variable, has no clue which particular term is being bound to that X. It's coming from somewhere, you have no idea. And in particular, the intruder can send you arbitrarily large terms. Now, there are two sources of unboundedness that we have mentioned here. 1, 3 at least, right? I mean, bound on the number of sessions, bound on the number of nonces, bound on the size of terms. Well, these are not completely independent, but in any case, each of these sources of unboundedness contributes to the intractability of the security problem, rendering it undecidable in general. And this is, something we have known for a very long time. And so typically, we look at the problem where we assume that there are only finitely many multi-sessions. So in particular, the question that you look at is there a run of the protocol consisting of at most k sessions for a fixed k, which leaks a secret? And this is the question that you want to look at. And note that it automatically bounds a number of fresh nonces used in a run, but the intruder can still instantiate variables with arbitrarily large terms. So the problem is not easy. The problem doesn't become straightforward. And so how does insecurity with simply a term algebra? This is the standard one. I'll just present the standard idea of how you look at solve the insecurity problem in the case of bounded sessions. And then we go on to what formulas do. So the basic model, this is the Dolovyov model that we talk about, is the inference system, which has got a couple of construction rules and some destruction rules as the dual of that. Construction rules say that if you've got two terms T0 and T1, you can form a pair. If you've got a term and if you've got a key, you can encrypt. And analogously, once you've got a pair, you can split it and use one of the individual terms. And if you've got an encrypted term and it's inverse, then you can derive the term T. And of course, if you happen to have a term, you can always derive it. That's it. I mean, this is the simplest term algebra you can think of. And this is the inference rules. And from this, so basically at any point of time, when you receive a term, you can see what are all the terms that, new terms that you can derive by adding this. And what is called the passive intruder deduction problem is given an X and a T. Check if there is a proof, of the particular term from this particular set of this thing. This is a problem that is eminently decidable. And to a very quick idea of how you prove this, you have a notion of normal proofs. You show that if T is derivable, then there is a normal proof of it. And then you show that good thing about normal proof is that any term that is occurring in a normal proof is actually a subterm of something actually mentioned either in the left-hand side or in the right-hand side. And having done that, you derive bounds on the size of normal proofs from this observation. And what are non-normal proofs? Well, something like this, right? You used the axiom rule twice, did a pair and then a split. It's completely wasteful, right? You could have directly derived T. Or another one, you first take T and K, encrypt it with K, and then use, K inverse I should have written, and then decrypt it. Again, you could have simply got it directly, right? So the idea, this thing is specified by having proof normalization, rules for proof normalization, which says that, for instance, here the only one that the two rules that I need are, if I have a pair followed by a split, right, that can be, simplified into one of the ones that you started with, the pi1 itself. So to derive T, you don't have to go through this torture, right? Similarly, you have a pair and this is not a pair, this is encrypt. Yeah, sorry. If you have an encrypt and then followed by decrypt, you can replace it by directly. So normalization tells you how to compress proofs. And then I said you have a subterm property which you prove something like if pi is a normal proof of t from x and r is some term that occurs in this proof, then either r is a subterm of the left-hand side or it occurs in t, or it is the case that the proof ends with some destruction rule such that it is actually from the left-hand side. So, and the idea is that you start with some proof by one. For instance, if you have an encryption rule, if R occurs in pi, okay, look at when R occurs in pi 1, it's certainly in subterms of this by induction hypothesis. If R occurs in pi 2, it is in subterms of the right-hand side, again, of the second proof by induction hypothesis. So if R occurs in pi, it must come from one of these things, either of these or in subterms of T encryption. Okay. Well, the other possibility is that if it's a destruction rule, I'm just doing a case analysis. You can, the other cases are all similar. Now, if R occurs in pi 1 or pi 2, it's clear that R is in the subterms of these. Now, pi is a normal proof, so pi 1 cannot end with an encrypt rule because we have a decrypt rule here. So it ends with some destruction rule, in which case by induction hypothesis it belongs to subterms of x, and therefore any R occurring in pi is in subterms of x. It's coming only from the left-hand side. So this is a very simple proof, but it shows that the height of a normal proof is bounded by the number of subterms in both x and t. And this gives you a polynomial time algorithm. You start with the given set of terms. In every step, you add all the terms that you can construct one at a time, and then you check if t is there, and you need to go only up to n, right? So n is linear in the size of this, and you can. So it's actually a polynomial time algorithm. So for passive intruder, you have a polynomial time algorithm, and you lift it for the active intruder. This is for the insecurity problem. So substitution. So when you go to the active intruder or the network and insecurity, substitutions and interleaving of sessions is at the heart of the problem, right? So suppose I have a protocol with two roles, eta 1 and eta 2. First one is some dummy term to simply start it off. So it's, let's say that some k public key of A, if you like, and then the second term some fresh nonce that this player picks and encrypts it with the public key of B, the whole thing paired and again encrypted with B, right? Now, what is the second role? Okay, it's parameterized by X and Y. It says, supposing you receive a pair of this kind, right? Decrypt and then pick the second term, decrypt it and send it encrypted by the first term. This is what it says, right? And now the intruder can learn the secret M, when you can take 3 sessions. So the first session and the second session with some instantiations x1, y1, and the second one with x2, y2, and interleave it with the substitution where x1 and x2 are both some k, the intruder's key, and y1 is this particular pair, and y2 is actually M. So I'm not going to go through this. It's a routine exercise to construct an attack and actually see that, this is the secret M is actually available to the intruder. Now, the points of interest are, for me, when I do this substitution for y1, I get a non-atomic term. And therefore, the first term received by B has larger size than intended in the protocol, right? So what it's going to do is it's a pair embedded in a pair, right? It's a long term. Y1 unifies under sigma with a non-atomic term mentioned in the protocol, which is of this particular form. So this pattern match is indeed needed for the intruder to get B to believe that sigma y1 is expected according to the protocol specification and thus elicit an appropriate response. The point is that this pattern match is the critical reasoning that is being employed by the intruder. If I take another example, if I take the same one, but if I consider a different substitution where I'm going to put a couple of paired terms in a pair, right? Now, such non-atomic terms are, they are also possible. You can consider these as, in some sense, potential candidates, but they are of little help to the intruder, right? Because if B, gets, what is B supposed to do? The receiver role, get a pair, second term encrypted, decrypted, and then you have the first one, and this is going to be encrypted with I. Now, intruder I can learn T, but that was already constructible by T. That is the point. I mean, by I, right? So T does not match any protocol pattern, so B cannot be tricked. So the main point is that if you look at the space of substitutions by non-atomic terms possible, some of them are critical for the intruder reasoning to be able to learn new secrets. Some non-atomic terms are completely useless, right? So in this particular case, the intruder might as well take this, by one to be some atomic term. Non-atomic terms are completely useless. So, and this is at the heart of a very nice technique due to Mikhail Ruzinovich and Turvani in 2003, where they show that the insecurity problem for when in the case of boundedly many sessions is in fact NP complete. NP hard is in fact the easier one in all these things. These are hard problems. The fact that you can do it in NP at all is what is the interesting one. And the main idea is that you call a variable good with respect to some substitution if it unifies with some non-variable pattern, but something that comes from the protocol specification under the sigma, and call it bad otherwise. So what are good variables? Good variables are those for which I need non-atomic terms, but they follow the pattern, right? It's a good pattern match from the protocol specification. So the idea is that you show that if there is an attack on the protocol which involves a bad variable, then one can zap it to some atomic value. I call it zap, okay, to obtain a smaller attack. And this is the idea that you can keep eliminating those bad variables. So you keep doing that, in the end, you will get all your variables are good. And what do you mean by smaller? It means that when I take that substitution and look at the size of the terms that are being substituted, okay, so, the resulting one has, is actually smaller in that sense. So once all variables are good, remember they are pattern matched from the protocol specification, and you can bound the size of such substitution by a polynomial of the size of terms obtained in the protocol specification. So this is the intuition that makes at least the Ruzinovich-Turvani algorithm, which is a very influential algorithm in this area, and you can solve the insecurity problem. So now comes the question, okay, now if you are going to extend terms by formulas, by assertions, right, of whatever form, how does this whole thing work? And this is what we're going to look at now. So I'm going to give you an outline of how you can extend this kind of ideas to protocols where agents can communicate logical formulas in addition to terms. Now, to highlight the difficulties, I'm going to look at an extension where you have only equality and only existential quantification, and that too only as a prefix. So you can write stuff like there exists x1, x2, x3, and so on, and then something with equality on terms, maybe conjunctions over that, that's all. The main point is when you start zapping variables, which as I said, to atomic values, which is at the heart of the NP procedure, equality between terms can get violated, right? So if I take a scenario like X is mapped to T and Y is mapped to some T encrypted with K, where Y is good and X is bad, you've got an implicit equality saying Y equals X encrypted with K. And this is going to get violated the moment X is a bad variable and you're going to map it to some atomic value. This is not true any longer, right? So you're going to have a problem, right? And so you can't do that. The real worry is that this equality is available to anyone. It's a communicated term, and you cannot zap it without modifying Y appropriately. So the original idea that patterns arising from protocol specifications, you just leave them as they are, is not going to work, right? So unification is going to work in more funny ways now. So, and what is interesting is now you have a basic problem with, remember the term algebra is extended with assertions. So you have to now extend the fundamental proof system as well, right? So now, suppose you have a run where you have some bad variable x and it's mapped to some encrypted term n with k. Now, the intruder may well derive n by decrypting. Somewhere k inverse shows up. Now what happens is when you zap x, we would like to mimic all the derivations that happen in the original run, right? Remember, I want to go from a run to a smaller run. And that's how I go to minimal runs, right? But the zapped image is now atomic, on which decryption can no longer be applied. So the intruder capabilities were there in original given run, no longer there. And that's a problem. So in general, situations where any kind of destructor, so I have talked about decryption here, any destructor rule is going to, when it's applied on a bad variable, need enormous care. And this is at the heart of the difficulty. And the equality theory also, brings its own complications. For instance, once you have a pair Mn equals M prime, N prime, if you can derive that, you can do projections. You can derive M equals M prime and N equals N prime, right? But the trouble is that if I have bound X to the pair M prime, where X is bad, now we have a proof of M equal to N by applying, when I bind X to N prime, right? So now if I zap X to get sigma prime, we can't any longer apply the rule on sigma prime X equals N prime, right? So the equality is violated. And similarly, so basically the idea is that when you derive an equality, either both should be good variables or both should be bad variables, right? And the other complication is that when a variable is good, it matches a pattern specified in the protocol. Now, therefore, we can view the pattern as a type of the term, right? We can think of terms having types, and the types are now, some product pattern specified by the protocol. So the intruder needs a variable to match a pattern from the protocol only in situations where it wants an honest agent to look into the term and extract some component. You remember that two-role protocol that I presented? That's exactly what is done by the intruder, right? So where you send the longer term, so the poor second role player decrypts it twice and does the job, right? So any such a pattern, yes, it needs to be good and therefore typed. This is giving us a notion of a typed proof. Yes, Yana?
Right. So I have a question. So in this setting, in the protocols, the agents or the participants communicate formally. Basically, for example, as you said, like in zero knowledge, they make, instead of sending a message, the message is something, does it exist in X such that something, potentially, such that they communicate more complicated assertions. But in the messages that they communicate, I use the full logic with K or just a propositional logic with
no, nothing. You have terms. The language of communication is terms, equality on terms, with a string of existential quantifiers before. That's
okay it. But the problem that I'm trying to decide, it's still the same problem as in the case of Turiani and so on, which is insecurity, not another problem. Still insecurity, just that I communicate terms with potential equality in them.
Yes.
Okay, thank you.
And so to continue, so basically we need a notion of, a notion of typed terms gives you a notion of typed proofs. And this gives us the notion of typed proofs. And I'm trying to give basically the ideas of how this works. So what do we mean by typed proofs? Right, like I said, the intruder needs, I will already gone through this. So the idea is that in a typed proof, all the good variables have a type, and any term that cannot be typed, you have a typing algorithm and it comes and says, oh, this can be typed and this is the type of it, and this cannot be typed. And okay, this we can show this is something you can do. And if it cannot be typed, it means that it must be built from components by the intruder, right? And this gives us the clue as to how to do the inference. And quantifiers, what is the kind of mess that quantifiers bring in? And this is at the heart of the problem with respect to complexity. If you have a formula, like there exists some string of variables such that t equals u, to derive such a formula, I need to apply the existential quantification k times. Collecting all the pairs that occur in such a derivation, x1 is bound to some u1, or w1, x2 is to w2, etc., that will give you a new substitution mu, right? And so proving this assertion amounts to proving the mu substituted terms are equal in some equality theory. And this is our heart of our idea. Unfortunately, there is no bound on the size of these witnesses because this is just an existential quantifier, right? So we need to zap some of these values as well. If you want to solve the problem, algorithmically, you'll have to find some ways of zapping these. So not only the ones that occurred, so originally, Rusinovich Rani tell you how to do that. And what I'm saying is that equality brings in its own mess, and you have to do some more typing, etc., etc. Quantifiers bring in one more source of unboundedness, and we need to show how to handle them, right? So now let me point out that there is considerable work on symbolic verification for security with equalities arising from some equational theories. The main point is that in these analyses, equality is in the meta theory, right? It is in the derivation system that you are using. And typically, you take the equalities and turn it into single ones and you term rewriting systems to do the analysis. In what we are talking about, equalities have the same status as terms. So equalities and existential quantifiers are first-class objects enjoying the same status as terms, and they, of course, then can be governed by equations in an appropriate equational theory. We do it using inference rules. And there's one critical thing that comes in this is that you have to ask when can I introduce an existential quantifier? When can I abstract away? When is a term abstractable? And this is something that's fairly important in what we do here, right? And you have a notion of abstractability. So you basically have to go into a term and ask, okay, here, can I abstract away from this subterm, right? And okay, so this is something that we do. And then the quantifier rules, existential quantifier introduction rule and the elimination rule. Elimination rule is kind of standard. It says if you have derived, there exists x alpha. And assuming that you've got x as a term and alpha as an assertion that you've already got, you can derive gamma, then you can derive gamma. This is the typical, intuitionistic form of existential elimination. And introduction says that if alpha holds with a constructible term t, and you can derive t, then you can derive there exists x alpha. Now there is a side condition here for that C out there. What it says that it be a constructible witness. So if you look at all the abstractable positions, C is something contained in that. It's all abstractable appropriately. So abstractability plays a crucial role. Maybe I'll skip this because I'm not going to use this, but main point is that you need some appropriate notion of abstractability and constructibility of terms. So the key ideas for solving the insecurity problem are as follows. What you do is to first you transform any proof to one where all the formulas in the theory that you're deriving in consist only of atomic formulas. And then you have an equational theory, but you have to make sure that it's consistent. You don't have junk like, pair is equal to encryption and so on. That is not very difficult. But then remember, equalities propagate, right? So in general, like you put some appropriate conditions and then you show that, given to decide whether a formula is derivable from set of terms and some set of certificates or formulas, what you need to do is to guess an appropriate substitution mu which has some particular properties and then check. This amounts to basically guessing a witness for every basic variable x in alpha. And the difficult part is in this entire analysis is placing a bound on the size of witnesses for this guess out here. And so what we can do is, okay, then there is a size bounded substitution satisfying the same conditions. But unfortunately, then you have to prove that that these preserve the same equalities, and a lot of work goes into this. And this is, of course, done using proof normalization. And I'm not even going to present the normalization rules. Okay, that's, a lot of technical work. So the main theorem says that insecurity with assertions remains in NP. And what we can show is that if you take any substitution, any term T, which is not coming from subterms, right? There is no anchor. Then must appear in some received assertion data first, and then it's generated by the intruder putting information together using a normal proof. And that helps us, very similar to what I showed initially, but with a lot more detail, right? It cannot end in a destructor rule, it must end in a constructor rule. And that allows us to convert every proof to a normal proof, or in addition, of a well-typed proof. And then typed proofs, we can show, help us preserve derivability even after we zap variables. And it gives you a notion of minimal variables from which you can calculate bounds. Okay, so this is basically the flow of how this entire thing goes. Having done that, okay, then you can say, okay, that is the minimal syntax. You can have a richer syntax. You can have some special atomic predicates. You can have equality you can have conjunction. You can have not only quantifiers, list membership, and something like, principle A says something is true, and so on. And then you can specify, you can model interesting protocols. For instance, we were doing the foo e-voting protocol, and we showed this. And it gives you a fairly nice abstract mechanism for zero knowledge terms. I mean, vote secrecy, for instance, is written, there is a parenthesis missing here. Yeah. And so what you are saying is that the vote is encrypted with P, and that is equal to X encrypted with Y, where X is actually equal to V, right? I mean, there exists X, Y, and so on. And it can be seen that proving such properties might involve considering multiple runs simultaneously, but the specification itself does not refer to any notion of equivalence. I'm saying this because in general, these things are studied in the literature, principally using equivalence notions, equivalence on runs. There are static equivalence, there are other kinds of equivalence study. And so finally, what have we got? Right? We can extend the language of communicable terms with quantified assertions. This is the summary, while still retaining the complexity of the insecurity problems for protocols with finitely many sessions. Now, in terms of logics for security protocol, our message is that considering first order logics, but with highly restricted use of quantification is in fact helpful. So the right abstraction is not a propositional logic, but a quantified logic. But where the quantifiers, we need to restrict quite severely and in a typed sense that logicians talk about. And remember that I'm talking about a positive logic of terms with no negation, no universal quantification, and only a very restricted form of disjunction, like the list that I said. And we, in fact, would like to suggest that when we talk about intruder theories, the left-hand side, which is, in this derivability problem, you can use universal quantifiers, but the right-hand side and hence communicable terms use only restricted to existential quantification. I can explain why we say that, but basically this is the idea. And the interaction between the quantifier and disjunction is really deep. I mean, it seems to have very crucial effect on complexity. And so these are all logical questions to study. Okay. So in this end, what I want to say is that if you want to dig into underlying reasoning in security protocols, something like these kind of communicated terms show exactly where the problems lie. And reasoning with equality theories is central. Reasoning with equality is central in security protocols anyway. And the existential quantifier captures the essence of what happens with encryption and not being able to look inside patterns. It seems to capture the logical core, but the way it interacts with other connectors is very complex, and we need to pin down and look at the logic of right expressiveness so that we can reason with protocols of that kind. So the point in all this is to keep the specification language as simple as possible with very little machinery. You do all the work in the analysis. In the analysis, yes, you've got a lot of work to do. Thank you.
Thank you, John, for a very interesting talk. I would open the floor for questions. I'll wait to see if there's any question. Please just make yourself known. No question that I can see. I have a series of questions. So if I might ask, first of all, do you just prove that this case of communicating terms with equality or equality checking, do you prove it still stays in NP as per the normal insecurity problem by Rusinovich and Turiani, or do you give an NP procedure for this?
Yes. No, we do give an NP procedure.
Okay.
NP procedure for that, and since the problem is NP hard already, it's even without the assertions, it's NP complete. Yes.
Okay. All right. I have another question, which is, you said that you can only handle sort of restricted sort of disjunctions, such as iterating possibly over a finite list or something like this, list membership. What is stopping for full disjunction here? What is the problem?
So the problem is that the only kind of decision procedure we can think of goes to p-space. I mean,
oh, I see. So you want to.
It has implications on complexity, not on.
Not on the.
Of course, that doesn't mean that that's a it is.
Yeah, because in finitely many session it should stay decided. So I see it is just the complexity. Okay, fair enough. Okay, to stay in NP, you need this restricted disjunction. And I have one last question. Is this not the same as equality testing in sort of applied pi if you consider that the agents have frames, and then you do equality testing over frames or whatever, static equivalence, let's call it, over frames? Is it not the same, or is it more expressive?
So certainly, having equality in the term algebra is more expressive than in the meta theory, right? So
possibly, yeah. In the general term algebra, yes, I don't know yours, yes.
Yeah. So I mean, even with the minimal term algebra, you can see that there are a lot more things that can happen in the frame in general.
Yes.
What we are saying is that there is increased expressiveness, but no price in terms of complexity. I mean, that is, of course, NP is a huge class, so right. So it's not, but certainly in terms of expressiveness, you do have, you can say more things about the frames. I mean, basically, what are we talking about? At every state, you are you're communicating not only terms that you construct, but the patterns that you can see, that you can assert on the terms, right? And those also are communicable. You're, communicating more information that you have got. Right?
Yes. Yeah, and I guess your equality assertions would equate to this equality testing in applied pi, but possibly your assertion can express more than that, if I'm correct.
Yes, remember, there are quantifiers. Right?
Yes.
Remember, these are existential quantifiers hanging around, right? So there's probably a map between these quantifiers in the thing and equivalent frames, equivalent runs. So, but equivalence classes of those.
Okay.
So that's why I said, rather than talk about properties in terms of some equivalence, right? You can directly specify, your properties don't have to say anything about equivalence and runs, etc.
Yes, I agree.
Yeah.
I have one last question. Actually, I have more, but I can ask you also offline because I'm aware of the time. So you said at some point that you can express things like vote secrecy, for example, in electronic voting, and that's the sort of expressivity that you've been looking at. Is it just an example, or I can see that you can express possibly more than just secrecy?
It's just that each of them will take like one slide to express, so I didn't go down. But pretty much I mean, it's only the e-voting protocols that we studied, but that we actually looked at all the, standard properties, and we can talk about. And as I said, in general, it's very simple, and there are no conditions on equivalences, etc., etc. It's just simple logical specifications that you've got, and it's something like zero knowledge terms, right? You don't have to extend the term algebra at all, right? It's simply equality, and that's it. Projections and equality is all that you need.
Okay, well, I don't see any hands raised, and we are now on the hour from when we started. So I'd like to thank Jam on behalf of UKSPS and FMSec and all of you who attended the talk. And for those of you who want to recheck the details, it will be available on YouTube shortly. Thank you, Jam. Thank you for a very nice talk.
Thank you very much. Thank you.
Thank you. Bye for now. Bye, everyone.
Bye-bye. Thanks, Jam.